Hello everyone. Today is the year 2026, month of June, 19th day Friday. I'm introducing a trending article from the archives today. The title is MagpieTTS LF inference-time long-form speech generation without training on long-form data. The corolla is Tortoise code 26F6.18485 on. It is long. Well, I once tried to teach an actual magpie to host this radio show, and it just stole my shiny microphone and flew out the window. Yeah, nobody ever understands my word jokes. Alright, let us dive right into this fascinating paper. Text-to-speech technology has gotten incredibly advanced lately. If you listen to short clips of AI voices, they sound perfectly human. Models like Tortoise and VoiceBox, amazing, but they only work perfectly for short audio clips. Usually, they are trying to generate speech that is only 2 to 20 seconds long. The problem starts when you want them to read something longer, like a whole paragraph or a full page of text, in generating longer length speech. These systems run into major issues. They suffer from something called Prosodic drift. This means the voice slowly loses its natural rhythm, and it might start speaking too fast or too slow. They also have speaker inconsistencies, where the voice suddenly sounds like a completely different person halfway through the text, and they have sentence boundary artifacts. This is when you hear weird glitches or sudden drops in volume, like between two sentences. To solve this problem before, people would just chop the long text into single sentences. They would generate audio for each sentence independently, and then just glue the audio files together. But this naive chunking strategy produces characteristic artifacts, including energy discontinuities and warbles at the boundaries. It also ruins the overall emotional flow of the speech. You lose precedent, patterns like intonation shifts, which makes the whole thing sound very robotic and disconnected. So, what this paper is trying to solve is this exact problem of long-form speech generation. They want to make a very long text, without losing the natural flow, or without changing the speaker identity. And the most interesting part is that they want to do this without retraining the entire model on long-form data. Retraining a huge artificial intelligence model costs a massive amount of money and time. So they present an inference-time approach called MagpieTTS LF. This means they just change how the model generates the audio, rather than changing the model itself. This approach introduces 3 key innovations that I find super interesting. They use something called soft attention priors, and a model reads text. It uses an attention mechanism to focus on specific words. Other stream methods used binary masks, which create hard information cutoffs. It is like putting blinders on a horse, so it can only see the card sentence and nothing else. And MagpieTTS LF uses soft priors. These soft priors maintain non-zero weights on past and future positions. This allows the model to preserve a graceful gradient of attention, meaning it slowly fades out its memory of past words, instead of completely forgetting them instantly. This helps the model retain long-range information, while still focusing computation on the locally relevant positions. Second, it created a stateful inference algorithm. This algorithm maintains context across sentence chunks, and it moves from one sentence to the next. It carries over the attention prior states and any other hidden states. It also carries over the text history. This creates a smooth continuity between segments. The model basically remembers how it was speaking at the very end of the last sentence, so it can start the new sentence with the exact same tone and energy. They use history-aware text encoding. They pass the past text history through the text in order to help with discourse-level Prosodic planning. This means the model understands the context of the whole paragraph and uses its native text representations to plan how it should sound. Let us compare this with other technologies out there. The literature shows 3 main ways people tried to fix this before. One way is sequence compression. Models like Vega Voice reduce the number of tokens per second of audio to fit more speech into a fixed context window, but this sacrifices temporal resolution. It compresses the audio so much that it loses clarity. Another way is using state space models for theoretically infinite extrapolation. And the third way is streaming in blockwise methods, which deploy blockwise attention masks. But all these other streaming approaches require training time architectural modifications. We have to build the chunking strategy directly into the model from the start. MagpieTTS itself does not need any of that. It operates entirely at inference time. The researchers ran extensive experiments to prove their method works. They evaluated it on a dataset called long-form chiffets, which they created to measure prosodic continuity and speaker persistence. They compared MagpieTTS LF against state-of-the-art models, like inference-time and VoiceBox. The results were honestly quite shocking. They measured the word error rate to see how intelligible the speech was. Our proposed method achieved significantly lower error rates compared to all other systems. Models that rely on aggressive compression, like VoiceBox, showed significant degradations and higher error rates. MagpieTTS also maintained the highest and most stable speaker similarity. This means the voice sounded like the exact same person, from the first second to the very last minute. Other models exhibited higher variance and drift over the sequence length. They also measured the energy drop at the boundaries between sentences. MagpieTTS itself had an energy discontinuity of just 14 decibels, which is roughly half the energy drop of competing models. It suffered from severe loudness inconsistencies because it independently normalizes the gain for each chunk. Now let us talk about how this amazing technology can be applied to everyday life. I will give you 3 specific application examples based on the content of this paper. The first application is the automated generation of audiobooks. Right now, recording an audiobook requires a human voice actor to sit in a studio for weeks. If we use standard AI to generate the book, the voice will drift, and the emotional tone will randomly change between chapters. With MagpieTTS LF, publishers can generate entire books automatically. The technology ensures that the speaker consistency is maintained over multi-minute durations, and the Prosodic continuity remains completely natural across all chapter boundaries. This would severely reduce the cost and time needed to produce audiobooks, making literature much more accessible to everyone. The second application is for personalized news, reading, and long-form podcasts. Imagine you have an app that curates long investigative journalism articles for you. Want to listen to them while commuting? The AI writing the news has weird glitches and robotic pauses between sentences. You will get annoyed and turn it off. Because this method uses stateful chunk generation to eliminate boundary artifacts, the newsreader will sound completely human. The soft attention priors will allow the buyer to understand the context of the whole article, delivering the news with the correct pacing and serious tone required for long articles. The third application is the development of virtual AI lecturers and lecturers. Online education is becoming huge, and students often need to listen to 30-minute or hour-long lectures. A virtual AI teacher needs to hold the attention of the students. If the AI suffers from hallucinations or repeats words because of alignment issues, the students will lose focus and fail to learn. The inference-time soft attention prior mechanism in this paper guides the auto-regressive generation toward long-term alignment, preventing any hallucinations or skipped words. This means the AI can give a flawless, human-sounding lecture that perfectly matches the educational material. It will have a massive impact on the quality of automated online education. Now, this paper truly shows that we do not always need to train bigger and bigger models. Sometimes, a clever algorithm in inference-time can solve the biggest problems in speech synthesis. The ability to generate coherent long-form speech without model retraining is a huge step forward for the industry. Thank you for listening to my deep dive today.